So therefore, we now define something called the ensemble average. So how do you define the ensemble average? Let us say A is a thermodynamic quantity and we want to get the ensemble average of A. So the ensemble average is usually depicted as this within bracket and ensemble. So ensemble average of a thermodynamic quantity A can be expressed as drn, where r, as I said, the coordinates of each constituent in the system, and n is number of particles, dpn. So I need to have two integral, one for r, one for p, and then a, this a, rn, pn is basically the instantaneous value of a in each microstate, and then we should have the rho rn pn, where rho is called the probability density. So rho is the probability density, and this rho can be defined as e to the power minus h rn pn divided by kt, again k is the Boltzmann constant, divided by q. Here here h is the total energy, which is the Hamiltonian of the system. Hamiltonian of the system, which is the total energy, is equal to kinetic energy plus the potential energy of the system. So h is nothing but the total energy of the system, and q is the partition function. Q is the partition function, and that q can be written as drn dpn e to the power minus h rn pn by kt. So this is the partition function q. And so basically, when you take the ensemble average, the concept is very similar what we have seen in the Boltzmann statistics, but how we improved on here in the ensemble average is that when we take h, so we have the interparticle interactions, as we'll see later. So interparticle interaction has been introduced in our formalism through the potential energy. So through this u and then to h, the Hamiltonian, we have introduced the interparticle interactions into the system, into our calculations. So that is one advantage, and number two is now we don't have to look at the 10 to the power n degeneracy that every state in the quantum system will have. Now, instead of looking at the quantum states, we are basically looking at each of the microstates as I defined here, and each of the microstate is basically defining the different conformation of my molecule of interest, or my biomolecule, or my liquid molecule of interest. And so basically by ensemble average, we are, since if you look at it, we have this probability density term, and this probability density term is basically giving the taking the importance of the conformations which are occurring more frequently than the others. For example, here out of many conformations that occur here, you can see that some of the conformations like this one, they are occurring much more frequently than this particular conformation, and therefore when you take the ensemble average, you will get the microstate which occur more frequently, having a greater contribution in the ensemble average. And that was again the definition of partition function what Boltzmann statistics provided. So basically we have the same concept here, it's just that we have now get rid of the ideal we just now introduce the interparticle interactions, and also now instead of the quantum state we can just look at the microstates in terms of the different distribution or different conformation of my molecule. Now if you look at the definition of ensemble average, and we have the integral, and it implies that to get the ensemble average we need to generate enormous number of microstates as they appear in the ensemble. So when you talk about 1 liter of water, or when you talk about the conformation of the biomolecule or the water can have enormous number of microstates because the molecules are always in moving. So it is actually very difficult, rather impossible to capture all possible microstates in an ensemble because the number is just infinite. So instead of going for ensemble average, a simpler definition of taking the average is time average. So in the time average depiction, instead of instead of waiting for all possible microstates, we basically take the average over all those microstates which we can capture within a stipulated time. And so according to this time average, we can define a time as limit t tending to infinity, meaning our time should be large enough so that we can capture as many possible microstates as we can, and then we can basically limit t tending to infinity 1 by tau, and then we have time t is equal to 0 to tau, a the instantaneous quantity, Rn at time t, Pn at time t, and dt, which you can further simplify as 1 by m sum over m is equal to t is equal to 1 to m, and a Rn t P n t. So what this implies is where m is number of microstates or conformations. So basically time average is saying that within our stipulated time, whatever number of conformations or microstates we have captured, so conformations in the context of biomolecules. So time average is basically take the average of the property of interest, which is A, over the number of conformations we have captured in that time frame. So time average is basically a finite quantity. But here the catch is this time. So longer the time we take, more and more number of microstates we'll be able to capture, and therefore our time average will be very close to the ensemble average. On the other hand, if we don't consider many more microstates, there is a possibility that we are neglecting the microstates which might occur at a later time with more probability or proportion. So when our time is long enough, the time average and ensemble average should converge. So a situation where my ensemble average is equal to time average, this situation is called the ergodic hypothesis. This is called the ergodic hypothesis, where ergodic, the scientist said that explore your system for a long enough time, and then your time should be almost equal to the ensemble average, because ensemble average is the ultimate target where we should explore all possible microstates, and then if we take average over all the microstates, we get the exact average value of the thermodynamic quantity A.